We were notified somebody left a purse in the restaurant. If anyone is missing their purse, go back and get that at the restaurant. Good afternoon. Thank you for joining us for the afternoon session of Design Challenge. First up this afternoon from Texas A&M, we have Team Prometheus.
Hello, everybody. Thank you so much for coming in after lunch. We really appreciate it. We are Team Prometheus. We've done lunar engineering and a nuclear reactor's CONOPS.
Hi, my name is Arnold. I'm a mechanical engineering major with a minor in mathematics.
I'm Isabella. I'm doing a major in bioenvironmental sciences and minors in geology and geophysics.
My name is Andrew. I'm an aerospace engineering major with a minor in mathematics.
So a little bit about our namesake with Prometheus. We wanted to go with the sort of Greek mythology route that we tend to with NASA. If you're not familiar with that, Prometheus stole fire from the gods to give to humanity in the form of technology, knowledge, and civilization. And we see our goal of providing power to the moon as analogous to this story. In doing so, we are providing a sort of light, this power to create opportunity for human presence on the moon to be further expanded and bring new knowledge to humanity.
So over the course of the past few months, our team has been developing a concept for a fully commercialized lunar economy. This lunar economy in question will contain key systems such as a lunar railway system, robots used for mining assembly, and habitats and other key infrastructure that will allow for resource extraction and distribution. This economy would be based around NASA's main region of interest of Shackleton Crater. Shackleton Crater is a permanently shadowed region, meaning that no sunlight reaches the majority of the areas, allowing for presence of water ice underneath the surface. If we were able to extract this regolith and extract the various elements from the regolith like water ice, we can use it for various commercialization and habitation opportunities. Additionally, the rims of Shackleton Crater face near continuous sunlight, meaning that we are able to use solar power around those rim areas. So a quick recap about Shackleton. It's a permanently shadowed region, meaning that no sunlight reaches those areas. Because of this, doing mining operations within the crater proves especially difficult with just solar power, and because of that, we are required to use a nuclear fission reactor. It's just a quick topography map and a map of the various regions of interest that NASA has for Shackleton.
So our lunar economy, as you see it, has 5 phases, including a phase 0, which functions as an initialization phase. Phase 1 would begin with the first Starship landing on the lunar surface and last roughly a year. Phase 2 would mostly consist of expansion of the rail network as well as the solar capabilities. Phase 3 of the project would be when we were talking about entering Shackleton Crater, which is when a nuclear reactor becomes necessary. Of course, we'd be entering to pursue the mining of water ice specifically. Phase 4 would function as another expansion phase, and phase 5 would be the finalized lunar economy. Essentially, just to recap of that. So as you can see, starting with phase 3, our power needs start to increase significantly, especially with the training. This is because we're talking about an expanded presence on the lunar surface, human presence. And we've identified a nuclear reactor as the ideal solution to this problem. This is because of the high power density of nuclear power systems in general. They are incredibly high power density for their dimensions, and they would also provide thermal stability to our surface systems. They're also incredibly reliable and long-lived, right? So we envision our system to produce power for like 10 years before needing a fuel. Another benefit of the system is it would allow us to be very minimally dependent on solar energy, which of course is susceptible to dust, solar flares, other issues, And of course, having nuclear power would allow us to traverse deeper into the permanently shattered region of the recycling grid.
You notice the logo there. We'll get to that in a second. So specifically, I want to talk to the importance of the reactor that we've chosen, specifically a microreactor. If you're not familiar with it, microreactors are very important. They're very compact, they're very efficient power sources for us, especially for something like this. In the context of space, they have been identified as highly desirable for future infrastructure, particularly with something that is going to be permanent, human habitation, satellite power, the future of nuclear propulsion and nuclear electric propulsion. But we also have the in situ resource utilization, which is something that NASA and corporate partners have also emphasized as part of their builds. So we have our decision matrix up here, which is something we built as a team after we identified our top 3 contenders in our design process. That would be the Westinghouse Astroventi, the Rolls-Royce microreactor, and Hermes microreactor. And after preparing some weights for our selection criteria, number 1 being safety, following our technology readiness and our power output, we decided that the Rolls-Royce was the one for the job. And there's a couple different reasons here. Some of the design considerations with the Rolls-Royce is the structural frame, specifically our housing for this, the titanium or aluminum for that lightweight material. It's very strong structure, and there's a lot of hereditary design surrounding that. We have reflective coatings as well for radiation mitigation, so silver or aluminum reflective coatings to reflect that solar radiation and prevent issues thermal in the future. We have the overall radiation management, which will hopefully be a directional shielding or a dual wall design for that insulation, and then the insulation of the car itself. So preventing temperature fluctuations, especially during those really rough lunar night periods. There's a couple more design considerations here, which is that core structure. So using single material blocks for that strength and integrity of the design for efficient heat removal, especially talking about brutal solar power. The control drive mechanisms, which is just the moderation and absorption of those materials to adjust the neutron flow and the reactor reactivity, giving us control of our power output. We have the heat pipes as a passive heat transfer here as well, and the gas turbine for the power generation, which will be a closed cycle system. So this will use the reactor heat to drive the turbine, essentially draining our electricity, but also allowing opportunities for us to harness excess power. There's a difference between the microreactor and the small modular reactor, which is important to discuss, especially after seeing our decision matrix. So microreactors are great. Small modular reactors are also great. They use slightly differing technologies used to power very different things. The microreactor in this example is 1 to 10 megawatts of power for its output. It's very compact and it's very transportable. A small modular reactor is around 0.5 gigawatts. It has to operate from static site. Once it is established, it cannot be moved or very well altered.
So the Rolls-Royce nuclear reactor would be powered by TRISO fuel, which essentially consists of small pebbles of uranium surrounded by layers of graphite and silicon. This allows for a controlled reaction within that also vastly mitigates the risk of a meltdown, basically makes it impossible. And then here we have kind of just an outline of the time cycle for reactor operations. Assuming that lunar surface operations will be based on universal standard time, we want higher risk activities such as mining to take place during astronaut sleeping hours, which means that power can be allocated differently during those times.
So a quick concept of operations and how we're going to actually integrate this microreactor with our whole system. The SpaceX Starship will load this microreactor onto it and land on the lunar surface. When it lands, it'll conduct various operational checks before finally sending a signal to unload the reactor. Then the automated systems within the Starship will load the reactor onto the Starship elevator, which will then lower the reactor down onto the lunar surface. From there, we go to actually place the reactor onto our lunar train. So in this case, we're going to be using our lunar crane to pick and place the reactor and put it down on the lunar train. And then we go to our next stage, which is the installation stage. And this stage, we're going to be basically connecting the power cables of the reactor to the train power system using an assembly robot. And then the final stage is the testing stage. In this stage, we're just going to be gradually ramping up the power of the reactor until it reaches operational power, from which we'll resume normal operations of the train. That's the testing stage. And this is the quick interface diagram of the different components of the reactor. There's the reactor, the closed cycle burning engine, and the train. There's various different electrical, mechanical data, and thermal interfaces that come between them. And you can kind of see how they interact here.
And so with this, we've identified a few requirements. We have a requirements tree that reads left to right, starting with our level zeros. We have a safety requirement, which goes without saying, human safety is paramount to the ability to complete a mission, build infrastructure like this. We also have a transportation method identified, the train integration, and a redundant power supply. On that, we have our emergency shutdown, containment, discovering things that we didn't think about before initially in the project to talk about that launch durability and that power contribution. And so with that, we have emergency protocols. We have a 7-step protocol. The objective, of course, is to safely relocate this microreactor in the case of a meltdown, moving that from the critical lunar infrastructure to prevent those damages in the event of an emergency. This starts with an alert and assess, a detach and a roll initiation, the control roll to safe zone with guidance, the radiation and temperature monitoring, which moves us into the emergency shutdown, a post-incident review, and finally recovery. There's a couple of future considerations for us, which is the completing trade studies. We'd like to path our lunar infrastructure as well and see how that relates to our reactor, and complete a review of the moon's influence or lack of when addressing radiation spread in a vacuum. So we have a bit of a summary here. Of course, you know, Lunar Reactor provides that steady high density energy source. With a lot of these integrated safety measures in the future, we can support that sustainable development of the moon. And real quick, we just want to thank all of those who helped us with our team. Extend our thanks to Dr. Bonnie Dunbar, our space mentor, Robert Knuckles, and of course, our Texas A&M mentor, Anderson. Thank you.
Questions for the team?
So you talked about having a rather complicated path to get the reactor off the lander, and assuming there's a crane, and even those systems require power. So, and then you didn't talk about where you want to put the reactor. Is it going to be inside the crater, outside the crater, and some of the challenges of the crew servicing that? Can you explain a little more?
Yeah, sure. So first part, the power. The reactor is going to be coming into the phase 3 of the operation, meaning that phase 1 and 2 is where we're setting up the actual infrastructure. In this case, the power before phase 3 will be fully solar powered. We'll be having specifically Honeybee Lunar Saber towers, which will be powering a lot of our operations before then. As far as where we're going to place our actual reactor, that's going to be on the train itself. So this is going to be a mobile reactor. We're going to be putting it on the train itself, integrating with the train system, and moving it around the Shackleton area to power various mining operations.
So y'all were saying y'all wanted to get started with solar to build your infrastructure first. But my question is, how are you going to store enough solar power given that the lunar South Pole goes through 14-day Earth cycles of light and dark? So you would have light for 14 days straight, but how are you going to keep power stored for those 14 days of darkness?
So certain areas on the Shackleton connecting ridge actually experience daylight 95% of the time, like in general. So the 14-day night cycle is like certain points, but especially using our Honeybee Lunar Saber tower, or not our towers, but Lunar Saber towers, them being elevated makes accessing that solar power much easier.
Other questions?
I think like on the other one, same question, it wasn't about, I think we ran out of time. But a lot of these are assuming they have to take this terrestrial reactor, you will, right? But what about considerations about the launch and landing aspect, the vibration and G-forces and all of that? You probably have to modify this reactor heavily just to get it to the moon and land it.
So there's already been reactors in development for space. That's why I mentioned the Rolls-Royce microreactor. These things are being developed for space operations specifically. Things like a microreactor that is involved with a closed cycle Brayton engine. These things are using only like passive heat mitigation, meaning that the internals, there's not too much moving parts in them. So vibration and all those things that are in launch and landing won't actually affect the reactor that much.
Any other questions? All right, thank you, team. Next up, Team Nova from the University of Houston, Clear Lake.
Hello, everyone. We are Team Nova, and we are presenting our design for the lunar exploration rover for extreme terrain that would be encountered on the moon. We are composed of myself, Mario Adames. To the left of me is Eli Fuentes. Next to me on my right is Oscar Franco, and at the end is Diego Zuniga. This is all for the Lunabotics 2025 Design Challenge, which is a competition held by NASA in which different students, different teams enter, make a design with a specific purpose in mind, and then compete to see who has the best design. Now, the reason NASA holds this event is to inspire innovation and to seek innovation. Maybe somebody designs a system or a subsystem that's innovative enough for them to incorporate into their design, into their prototype. And if that's not the case, then it allows students to have real world experience in where they can apply their theoretical knowledge and to an actual design. Now, the specific task for the Lunabotics 2025 is to build a berm and a VERM. And a berm is just a hill or amount of dirt. And the point of this is the leveling that happens as a byproduct because NASA, well, they need flat surfaces to put up nuclear reactors or storage facilities or what have you. And all of this needs to be done under certain constraints, which will be further specified in the rest of the presentation. Here's a quick presentation outline, and now I'm going to hand off the microphone to Eli Fuentes to talk about project goal summary.
So for our project goal summary, we want to understand what mechanical systems are on lunar surfaces, and what that is also looking at the lunar regolith construction on this specific lunar surfaces, and then stress analysis on the robot itself. Then we also want to get exposure to robotic components, such as just the mechanical system on the robot and how it works. And then we also want to practice coding on software. Since mechanical engineers, we're not familiar with a lot of coding, so we want to get a little bit more hands-on on the coding aspect as we go on. I'll go ahead and talk about the project goals and criteria. For this project itself, we are tasked to build a robot that has the ability to transport a minimum of 0.5 kilogram of regolith, and also have a durability of at least 2 hours on a single charge. The frame has to have a maximum weight of 80 kilograms, and also construct using materials that are less resistant, which is an IPS6. And what this IP is an ingress protection, which is a range from 0 to 6, with 6 being the least resistant to dust. Also, we need to protect all mechanical and electrical components on the robot, concealing all electrical wires and electrical components that is visible to the naked eye. We also want our robot to run autonomously and to be remote controlled. That's where the coding aspect comes in. And also have an emergency stop button in case any emergencies or any mishaps on the robot. And finally, we have a maximum budget of $1,600 for the robot. I'm going to go ahead and talk about the HOQ real quick. And what I have here on the left, as you see, we have our customer requirements that I just described. And then we have the ends that represent the negatives that affect the HOP negatively, and then the P's that affect it positively, comparing to our competitors that are on the right side. Then I'll hand it off to Oscar to speak about our concept generation.
Thank you, Elias. So as you can see to your figure to your left, we have concept one. During brainstorm generation, we came up with two different concepts. The key components as labeled are the battery casing, frame supports, the frame, the sprocket drives, the caterpillar tracks, and the suspension system. As mentioned by Mario earlier, our whole objective of this concept was to build a berm, and we thought the easiest way to do that was through a bulldozer operation. Majority of this concept will be made out of 6061 aluminum, and it features an individual suspension system, which allows maneuvering through the regolith. This concept also features 4 DC motors that can be connected in parallel in order to power the robot. Next, we will be talking about concept 2. The major difference between concept 1 and concept 2 being the material selection. Concept 1, we chose to stick to 6061 aluminum, while concept 2, we wanted to build it out of polycarbonate shell. The critical components for this concept were the polycarbonate upper and lower shells, the 10-inch airless tires, the sandwich plate that connects the upper shell and the lower shell, and the bulldozer operation. Concept 1 weighed 60 kilograms with no electrical components, as compared to concept 2, it weighed 17 kilograms with no electrical components. Now, as a team, we needed to make a decision on which concept to further pursue, and we took into consideration the following criteria: the required torque, manufacturing, material properties, maneuvering, cost, accessibility, and weight. After taking careful consideration of these criteria, we decided as a team that concept 1 was the best out of both to further pursue. So I will introduce our technical content. We first started off our technical content by running an FEA analysis of our robot frame. As mentioned previously, concept 1 was made out of 6061 aluminum, so we decided to run 6061 aluminum FEA analysis with a load of 80 kilograms imposed by NASA standards. After running this test, we figured out that the maximum stress, according to von Mises, experienced by this frame is 0.427 megapascals, and when compared to the yield strength of 6061 aluminum, we get a factor of safety of 64. Now, we ran FEA analysis on our frame supports as well. These have differed from our original frame supports since the original ones failed under stress concentration at the center. So these are our redesigns. We assumed a load of 80 newtons applied to them since we have a polycarbonate shell that goes over concept 1 that weighs approximately 25 kilograms. And if we assume a perfectly distributed case, we get a resulting force of 80 newtons on this frame supports. After running FEA on this, we figured out that the maximum von Mises stress is 0.36 megapascals, leaving us with a factor of safety of 74. And these factors of safety let us know that we can reduce thickness in both the frame and the frame supports, leading to less mass compared to original mass. And now Diego Zuniga will continue guiding us through our technical content.
So for the technical content, we had identified physical parameters that would allow our design to function. One of these parameters or one of these functions is just the ability to move. To do this, our robot will have to overcome the max static friction force that it feels. We assumed a max weight case scenario of 80 kilograms. This provided us with a total friction value of 588.60 newtons, which we then used to fully define what the torque values of our DC motors will have to be. So the torque for the DC motors were defined using a general case of 10-inch diameter non-pneumatic tires. The radial distance of that would be the 5-inch, and this would then result to be 0.127 meters. And the torque, the minimum torque value that we would need in order to break static friction would be 75 Newton meters. Therefore, we would have to acquire motors, DC motors that can provide a higher torque value than this. Since we're using 4 different motors, we divided the total torque value by 4, and this would mean that we would need a minimum torque value for each motor for a total value, minimum torque value of 18.69 meters. With that now out of the way, we had to identify what would be the total amount of mass of lunar regolith that we would bulldoze. We first defined the width of the blade to be 400 millimeters. The team would want to dig at a total depth of 1 inch for a total distance of 12 inches. This then provided us with the total volume of regolith that we expect to excavate or bulldoze, and we multiplied that by minimum and maximum density values provided by NASA-funded research papers, and we used the maximum value to acquire a total mass of 5.759 kilograms. That's equivalent to 56.50 newtons being acted on the blade which you can see in the figure on slide. Following with that force calculated, we were then able to find out what would be the induced moment on the vital location that the team had deemed important. This would be the bulldozer and hinge assembly. We would find the safety factor for this assembly by defining all the stress values that is exhibit at this location. We would apply the MSS failure theory, and we would acquire a safety factor of 1.49. I'll now pass it on to Eli to talk about the project planning.
Thank you, Diego. For our project plan, we plan to finalize all CAD drawings by the end of December 2024, which is next month, doing all that tweaking. And then by spring of 2025, that's when we want to start building our robot. And that what that entails is pre-ordering materials, pre-ordering parts, and also performing quality assurance after it's built, and make any final fixes that we need to on the robot if necessary. Then we'll start assembling all wires and electronics by spring of 2025 as well. After we have built this robot, we'll include all the electronic components, the microcontroller, that way we can code the robot, and also follow all TSGC deliverables. Here's our Gantt chart that I'll go ahead and speak about real quickly. We have a product specification, our concept generation, embodiment design, detailed design, and production seen there. And on the bottom, you can see our dates for when we plan to complete this. Then I'll hand it off to Mario to talk about future implementations. Thank you.
Lastly, we are pretty much our next step at this point is to start picking and then buying our DC motors, our batteries, our microcontroller, and our transmitter. They're all going to be off-the-shelf parts most likely, but we do need a microcontroller and a transmitter to be able to navigate correctly. And to conclude the presentation, I know we just threw a lot at you, so let me summarize. We're going to go with the concept that was the lightest, that applies torque better, or more low-end power, and therefore we went with threads. Our main constraints were to stay under $1,600, to stay under 80 kilograms, and to meet the required torque based on our calculations. And then to finalize, we gotta finish the CAD drawings. We gotta tweak them enough to have the proper suspension. We don't want a suspension that's too soft, and we don't want it too stiff of a suspension, because we want to be able to get out of any jams that the Lunar rover may encounter. And that's our presentation for today. Any questions?
Questions?
So with your design, now you plan to, I'm going to piggyback off the previous question. How do you plan to offload this from a delivery vehicle to start implementing on the service?
So we want to make a program to where it could be easily maneuverable. So we would offload it by just using the remote control associated with it.
So that means that an astronaut would have to pick it up, put it on the ground, and use robotics to pick it up, put it on the ground. Does it crawl out of the vehicle? How does that happen?
No, it will crawl out of the vehicle by itself. That's the autonomous part we talked about. We do want to include some autonomous features on, so getting out of the vehicle would be autonomous.
Any others?
Sorry, just thinking out loud on the tracks with threads or wherever. You also saw the other presentations how the design really varies a lot with capturing, the friction and regolith, and so were y'all planning to test how well this thing grabs, or just kind of the future?
Yes, we were planning on prototyping and testing on BP1, which is a legal assembly, to see how well the tracks perform.
Other questions? All right. Thank you, team. All right, please welcome from Prairie View A&M, PantherTech.
Good afternoon, everyone. My name is Caleb Crawford.
And my name is Royal Williams.
And today we brought to you an IVGEN mini pH correction system. So just a little bit about what we're going to talk about today. We're going to go over a brief background as well as the objective of the project. We're going to go over some considerations we had to go over as well as the importance of the project. We're also going to go over some margins of error that we came across, 3 different concepts that we thought of, and then what our final concept that we decided was going to be.
Okay, going into the current IVGEN mini. So it consists of the fluid generation module, the filter box, and then potable water bag, and then the IV bag. So with this, it actually takes the potable water and it injects it into the FGM, and then it filters through the filter box. And then after the filter box, it will add the saline solution into the intravenous fluid and create intravenous fluids. So our objective for the project, we were created in testing and creating a system to create correction of the pH balance for the potable water. So with the IVGEN mini, we were able to make sure that it was safe. So it has to meet the USP standards. It's scalable. Since the IVGEN mini currently exists, we have to implement our design into it. Make sure that it's reliable. No one wants bad stuff in their bloodstream. This is IVGEN, and we want to actually protect and keep our astronauts safe and make sure that it's effective. And it's constantly able to monitor the pH levels of the water. So why is this important? So during the space travel, right, the IVGEN fluids actually support about 30% of the medical conditions that will happen out in space. So also, yesterday we heard him explain how we want to go further and have longer space travels. And to do that, if you're getting sick, we can't turn the whole spaceship around and come back to Earth for simple medical procedures. We have to work with what we have on the ship, right? And then also, the intravenous fluids have a shelf life of 16 months. So how can we further along that application process? Also, with the IVGEN fluids, even though we're putting it for the space travel, it also could be used here and in real world applications, right? So water treatment. We have to be able and be mindful of the pH balance that we are consuming. Agriculture, the pH levels of the water and the soil is very important for optimization of growth for different crops, right? Pharmaceuticals, food and beverage, we don't want to eat anything that has a too high of a pH or too low. Chemical manufacturing, cosmetic, and agriculture.
All right, so here we have some things we had to consider for our project. One thing we had to consider was the accuracy of the pH adjustment. Obviously, with our container, it might have different levels of water in the container, so that has to be brought into account when putting in the different acids and bases into the mixture, as well as the pH of the water. If the pH of the water is too acidic, is like really high in acid, obviously you have to add a lot more base. But if it's just a little bit too high in acid, you only have to add a little bit of base. So just taking that adjustment into account. Also, we have to take into account the reaction time the water will take to get a new measurement of the pH. How long it will take for the new acid or the new base to mix into that water. Next thing we had to take into account was the acid and base compatibility. We don't want an acid that's going to react bad in your bloodstream. We don't want a base that's going to react bad in your bloodstream because obviously that's just going to lead to different medical issues along the way. So we had to make sure those acid and bases were good for humans, as well as they won't react with the materials that we're using for our project. Because obviously different acids react with different chemicals in different ways. So we also had to do research into that realm. We had to make sure our design was compact in size, and we had to make sure all of the USP standard for pH of IV fluids, which is about a 4.2 to a 7.1 pH. Finally, we had to ensure that we had to look into the power of our system, whether that be our main power that we're going with, which would be solar power, or our backup power, which would just be battery power. And finally, we just had to look into the temperature that this could all be stored in. Obviously, this needs to be stored in a very dark and consolidated area with a temperature around 59 to 75 degrees. So the different things that we came across for our margin of error was obviously pH imbalances, maybe overshooting our pH threshold if too much of a base or too much of acid goes into the mixture. So we have to do, so that needs to be looked into very carefully. Component failure just in the electrical components and different things like that. Obviously things that happen in space. Fluid contamination, making sure no other minerals or no anything else gets into our fluid that could possibly just make it not good, not suitable for the human body. Obviously just the overcorrection of pH that I went over earlier. Human error. Obviously we're all human, things happen. That has to be considered into all this. The mass and volume optimization risk as well as microgravity effects. So these were our 3 ideas that we came up with for how we could filter our water as well as alter the pH. So our first idea was altering the pH before filter. The second one was doing them hand in hand, and the last one was altering the pH after the filter. Ultimately, we opted to alter the pH after our filtration system, mostly because if we altered it before and it filters, that could really change the pH and just make us have to go through the whole process again. So it just didn't really make sense in our eyes. Doing it during the filtration, we consider that the acid or base being mixed in could like just mess with the filter and not all the minerals and different things to be filtered out. So we ultimately opted to go with the post-filtration test to where all those bad things are filtered out of our water. And then after that, we test our pH, make sure it's adjusted, make sure it's all good. So when it comes to a design, we have our just a base world 3D model as well as our design that we brought with us today. Obviously, our design that we brought with us today, so a whole lot just electrical components, but we did want to make sure we brought a working type model to where our motors were working and different things like that. So just going over our design that we have over here, we have our water storage container with a blade on the motor at the bottom to make sure that water is always moving. Another benefit of having that blade at the bottom, make sure the bottom water is always moving, is having when those acid and bases come into the water, they get mixed in evenly. So when the pH is being measured, it gets an accurate measurement no matter where the pH sensor is at. So we have our pH sensor also in the water storage, and we have that on a clock. It's not continuously measuring the pH, but every 10 seconds we determine that would be suitable for it to measure the pH. And the reason we have that is because if it's continuously measuring the pH and the water is too acidic, it will continue to read that's too acidic and it'll keep adding more base and ultimately overshoot our pH threshold. So we want to make sure that with that 10 second delay, that's time for a base to be put into the water storage. It gets mixed in evenly, so our pH sensor can have an accurate reading. Also, we have our pH display that will display what the pH is to the user. And we have different pumps and different things like that that are going to bring the acid into the water source as well as the base into the water source, depending on the pH of the water at the current state. When it comes to testing, we thought of, obviously, it's going to take a while for water to have acidic or base pH. So we decided that it'd be best to take an acid and take a base that are already, of course, acidic and base it. And we can measure the pH of those using our pH sensor, and then that's how we can test our device to where if it reads it right, if it adds the correct amount of base or the correct amount of acid, it gets to that threshold pH that we want it to be.
Okay, on to the fun stuff, chemistry. I know everyone loves that class. So, about our pH correction functionality, right? So measurement, you have to measure to see if it is too acidic or too basic, right? So if it is too acidic, we're gonna add base in order to kind of neutralize and have a reasonable drinking pH balance, right? And then it will analyze the different levels as well. Adjustment, how can we adjust through these pH levels? And then, as Caleb said, continuous monitoring. So we don't want to overshoot and then have adding too much acids, because then it's still an acid at the end of the day. So if you're adding too much acid into the water and then it's going into your bloodstream, no bueno, right? And then the final check, just making sure that the acids are, or the water is at a functional level. And going into the chemical decision matrix, right, we ended up choosing dihydrogen phosphate, right? That is actually found in a lot of our food and beverages now. So that's kind of where I was going when I chose it and selected it, because it's already meeting the USP standards. The other ones just had different. They came short just a little bit. I know the last one it reacts badly with sodium hydroxide, which is our base. So that's kind of why I chose not to use that for that. Talking, but
So, in conclusion, we developed an automated device to generate sterile IV fluids in space by adjusting the pH of portable water to meet United States pharmacopoeia standards. We wanted to make sure that this had real world application so it can be used on Earth before it's even sent into space to really truly test, as well as we have it can be used for extending space travel missions. All right, we just wanted to, of course, thank Dr. Quincy Moore, our sponsor, as well as thank our NASA mentors, Justin and Courtney. And we'd like to thank, of course, Floor, who sponsored us today.
We have questions.
Your application was for doing this in space travel, correct?
Yes.
Have you looked into the cosmic radiations that will affect the water pH levels as well?
So currently, no, our research hasn't included like the different cosmic radiations that could be in space. I know that was saw a little bit, but we just didn't have the time before we came here to really implement that into our presentation. So we didn't want to talk about that and be incorrect before we complete our whole research on it. So as we continue this research, as we continue to make our device look better and work better, and all those the type of things, that will be something that will be implemented into the final presentation.
Overall, I just want to say it's a great presentation.
All right, thank you.
So what type of pumps will you use, since pumps can become corroded or clogged due to use of overtime? Since you did talk about, expanding the space travel, as well as the acid or bases, chemical compounds causing corroded pumps. And you talked about expanding time and space, but how do you supply the materials for those extended years that you want to become in space and traveling to Mars, etc.?
All right, thank you. So as for the pumps, I can't tell you the name of the pump off the top of my head, but I know we wanted to make sure that the materials we included could be easily replaceable, just for that lengthy space travel experience. Obviously, things can rust, things can go bad, and so we want to be able to replace those things on those space expeditions. And so, like you said, for the pumps and different things like that, it could need to be replaced as that goes on. So we made sure that the different types of pumps and different things would be not that expensive. It could be easily replaced.
yes, and to further talk about that is our person that actually researched the pumps and different material in the electric part. They're not here. It's just the both of us. But if they were, they can answer your question. I promise.
Good question.
I think there was a page right before the conclusion page, right? You had the two chemical, yeah. So the bottom one is to add plus H, I guess, to make it basic. So is the H2PO4, I'm sorry, miss, is that to acidify it?
Yes, that's our acid.
Okay. So the one thing, or maybe I missed it, is this system automatic where it'll adjust, depending on what you've got coming in as a source? It's got to detect, right, if it's acid or base, and then adjust what you put in it to get to the H ion level you want.
Mm-hmm. So we have, in the model, we have two pumps, right? So one side, this side, these are where our two pumps are actually located. And one pump would be for the acid, and then the other would be for the base. So it would know to turn on this one. Like the logic that we have running through the system would be able to tell, okay, we need to use this acid and calculate how much acid we need to add into the water.
Real-time adjustment.
Yes, so real time adjustment.
And it doesn't matter if those two different chemicals you're using mix.
Yeah, no, they react. They know that.
All right, thank you, team. All right, please welcome from Texas State, Team Effectively Grounded.
Hi, we are Effectively Grounded from Texas State University. Up here with me is Aiden Bachmeyer, Dan Bostayev, Alex Johnston, Josh Beniga, and Hunter Savage Pierce. So we were tasked with developing a radiation-tolerant crew laptop. We were tasked with developing a radiation-tolerant crew laptop to so we were tasked with developing a radiation-tolerant crew laptop. NASA is committed to going back to the moon, and they will need a radiation-tolerant laptop to do that. And Microchip is developing the high-performance space computer, or the HPSC for short, in partnership with NASA. The HPSC has not been released yet, so we did an extensive study of available RISC-V processors, and we selected the PolarFire SoC FPGA from Microchip. This chip has a microprocessor side as well as a fully programmable gate array. This allows us to implement hardware that's not physically on the board. And staying within the Microchip ecosystem allows us to ensure the compatibility between hardware and software when the HPSC is finally released. And now Alex will speak to us about the importance of radiation tolerance.
Hi guys. Oof. It's been a day, a lot of presentations. Why do we need radiation-proof electronics? One of the main problems that face electronics in space is high-powered cosmic rays hitting them and messing with the code. For example, here on Earth, we have a magnetic field that protects us. If we were sending code to Mars, for example, to communicate with a rover, I'm going to take my code, send it through space, it'll get to Mars and communicate with the rover. In this example, the rover is going to move off screen, do exactly what I told it to execute. Well, if we introduce radiation into this, if I sent that code to the rover, it is on that rover, what happens if radiation hits the CPU? It'll cause bit flips and cause the rover to execute commands that I did not tell it to do. And in worst case scenarios, it'll cause total destruction of the components, such as the rover running off screen. This is known as a single event effect. Single event effects happen when these high-powered cosmic rays come in, they hit the CPU and cause thousands of electrons to scatter. This can flip bits. In the most positive area is only 1 bit, but there's no determining how many that this could cause the flip. The real danger, though, is total ionizing dose. Total ionizing dose for electronics is the dose of radiation over time, and this can lead to total destruction of the components. To break off into our design, I'd like to introduce Josh. Here you go.
Thanks, Alex. So one of the first steps when designing a custom PCB or PCB printed circuit board is deciding on a design software. So for our design, we used Altium Designer. So Altium Designer lets us work on the schematic as a team simultaneously across different schematics. So with Altium Designer, we can do the PCB layout, schematic design, and prep for manufacturing all in one design suite. And for the implementation of the audio subsystem, there is no native I2S support, which I2S is the preferred protocol for sound. So instead, we would have to utilize the FPGA fabric and place an IP core to implement I2S and sound for the board. Going on to the camera visual, it would be easiest to place a USB camera into a USB port on the side of the board. Although this takes valuable bandwidth away from the other peripherals that would also sit on this USB hub. So instead, the PolarFire SoC itself actually has pins that support MIPI protocol. So we're going to break out these pins into MIPI connectors, and we'll connect our camera through a MIPI interface. And back to Alex.
Welcome back. The overall thing, there's a lot of facts that are up on that slide. The overall consideration for the system is we're going to be using 80 watts max in our final implementation. Power is a very finite resource, so it needs to be spared as much as we can. What really matters for me is the communication subsystem. If I open up a laptop, I expect to connect to Wi-Fi. Well, in our current implementation, I use clickboards, as shown in the top right. Clickboards click into the micro USB, and you can start running communication protocols through there. For our final design through Altium, I'm currently conducting a trade study on communication chips that will be utilized in our completed dev. Now, on to Dan.
Thank you, Alex. For our custom PCB board, we are going to utilize iSchool Kit development board, and we're going to use it as a reference design to implement our own memory and storage subsystem. The memory storage on our board will be 2 gigabytes, which is modest compared to typical laptops. However, it will be enough for our proof of concept board that will boot a Linux operating system. And for the storage solution, we're going to use SD card, and the storage capacity will depend on the SD card that we decide to use. However, we have a 32 gigabyte SD card in our possession that we're using with our development board at the moment. And I'm going to pass it on to Hunter.
Thank you, Dan. For the graphics subsystem, we are facing some challenges. The HPSC is currently lacking integrated graphics. Also, current space-ready GPUs do not fit our form factor. On top of that, there are also limited high-performance GPUs in the market for deep space flight. Now, while there is availability issues, the industry is growing, as shown in the photos. So what can we do? Well, we can establish graphics capabilities in the PolarFire system-on-a-chip and PCIe connections. We can do this because PolarFire offers PCIe connections via FPGA. This enables modular and flexible external GPU connection, which is perfect for the growing industry. And now, in the bottom line.
So for USB, the PolarFire SoC that we're using does have USB 2.0 support hosted on the CPU itself. To facilitate connections with multiple input peripherals, we're going to implement a 4-port USB hub that we can use to connect a keyboard and mouse, leaving us with an additional 2 USB ports for future expandability. Some things that we've accomplished this semester is we conducted a trade study comparing several RISC-V processors, and we identified that the PolarFire SoC would be the most appropriate for this project. We also progressed toward completing a schematic of our custom motherboard design using the iSchool kit as a reference. We managed to establish collaboration with Microchip and got some guidance from one of their systems engineers on our motherboard design. And a big thing that we achieved this semester was we successfully booted an Ubuntu distribution Linux onto our iSchool kit.
Speaking of our project pipeline, we already identified our solution pathways. We picked the processor that we're going to use as well as the development boards that we're using to test the feasibility of creating a main board for a laptop. So this is our current stage. We are pretty much done with prototyping. We were able to connect certain peripherals like keyboard and mouse. We were able to connect a USB host to see that we can support multiple devices as well as internet connectivity. Right now we're in the middle of designing our custom PCB schematic, and we will be done with it by the end of the semester. After that, that gives us enough time to create our own PCB layout in which we're gonna place all the components on our own form factor. The completion date for that is beginning of February, and that gives us enough time to manufacture the board. And we're gonna use a third-party company that will manufacture the board for us. Along with this, we're going to document the design details for the future teams or NASA engineers that are going to use our design to develop their own implementation of the radiation-tolerant flu laptop. And as soon as the board gets manufactured and delivered to us, we're going to conduct testing and validation. We're going to document the test results, and we're going to hand off our project to the next TSGC design team or NASA engineers. And we would like to say thank you to TSGC for holding this event. I want to say thank you for your support, and I want to say thank you to our principal investigator, Dr. Campo, our NASA mentor, Mr. Justin Batista, and our faculty advisors that were helping us with the design, Mr. Stevens and Mr. Welker, and as well our mentor team, Schrodinger's Bobcats. Thank you guys so much for mentoring us. And we are now ready for Q&A.
So the microchip is not the only part of the system that can be triggered by radiation events. So any of the electronics on the system, EMI filter, DDC to DC converter, even the wiring, the electrical traces in the circuit board could be have a problem because of radiation events. So in looking at and hardening the laptop, did you consider other techniques such as shielding and other mechanical design options, because getting rad hard electronics for every single one of those parts was going to really drive up the cost of that laptop?
That's a great question. Thank you. Unfortunately, we don't have a big enough budget to use the proper techniques to radiation harden our entire board. But yes, there are techniques in place for doing that. For example, using ceramics for traces and using military and automotive grades parts, little ICs on the board that are more radiation tolerant compared to the regular parts. But for us, the objective is to design a proof of concept board of, okay, it is possible to create a laptop with the RISC-V and structured set architecture.
One of the big things that you mentioned is that your product is radiation tolerant. What have you implemented into your design that you presented today to make sure that this product will be radiation tolerant?
That's a good question. We were thinking about creating a list of the ICs that we're going to use on the, or all the parts that we're using on the on our own custom PCB board, and then trying to find a alternative part that is also radiation hardened. And again, that goes into the documentation portion of our design. However, unfortunately, we don't have a big enough budget to facilitate the creation of the actual radiation-tolerant board. For example, RAD 750 that they're using right now costs $200,000. And I mean, if someone can donate us that money, we can try. But unfortunately, it is not possible for undergrads.
Any other questions?
So on that note, and let's say we have a budget here. You talk about radiation tolerance and some of the design considerations you have, along with testing that, truly testing that, verifying you're building the right thing, validating what you're building. How would your team go about doing that? Has that been a consideration for you?
That's a good question. Our team was not considering that heavily because we will not be designing the actual radiation hardened main board. However, I would imagine there would be heavy testing procedures, such as shooting it with the radiation that is similar to what we experience on the moon or Mars. And I think this is something that's going to be used for testing the hardware.
All right, thank you, team. Okay, we have a short break now. We will be back again at 2:40. With the second half of our afternoon. All right, welcome back. To kick off the second half of our afternoon, we have Team Pleiades from Texas Women's University.
Good afternoon, everyone. We are Team Pleiades from Texas Women's University, introducing the hypertrophic aid by limb occlusion, or HALIM device, to mitigate muscle atrophy in long-duration spaceflight. My name is Erin Rocha, and these are my teammates, Hannah Schnettler, Carolyn Scovey, and Micaiah Brittman. The fifth member of our team, Josie Salazar, was not able to make it today. Before we begin, we would like to take a moment to thank our faculty mentor, Dr. Rigby, and our NASA mentor, Dr. Reyna. To start, gravity plays an important role in eliciting stress on our weight-bearing skeletal muscles, such as the quadriceps, the gastrocnemius, and the soleus. This allows us to perform everyday movements required for our daily activities. In microgravity, though, these disused and unloaded skeletal muscles will result in muscle atrophy. In the first 5 to 11 days of spaceflight, astronauts will experience 20% size reduction in these muscles. Astronauts that experience muscle atrophy cannot efficiently perform their crucial daily mission tasks, increasing their risk of injury during spaceflight. Here's Hannah to elaborate more on the background of our project.
One countermeasure to mitigate the negative effects of skeletal muscle atrophy is exercise. On the ISS, astronauts perform resistance exercise 3 days per week, alternating between light, moderate, and high intensities, as well as alternating sets, repetitions, and rest periods. This can make it difficult for astronauts to remember the details of their training protocols. As you can see on the slide, intensity is quantified using a 1 repetition maximum, similar to what is prescribed on Earth. At these intensities, an increased risk of muscle injury can exist, as well as a reduction in muscle recovery. In order to promote muscle growth, muscle recovery, and to simplify exercise prescription, the technique of blood flow restriction may be used. Blood flow restriction is a technique that utilizes a cup-shaped device to occlude blood flow to an extremity by applying pressure to major arteries. This method is typically done at a low intensity, mimicking the benefits of high-intensity exercise, including muscle hypertrophy. During blood flow restriction training, it involves up to 75 repetitions across 4 sets, eliciting rapid muscle fatigue in the targeted area. Despite the low intensity of exercise and reduction in blood flow restriction training lowers the risk of overexertion, decreases prevalence of muscle injury, promotes muscle hypertrophy, and aids in muscle recovery. To summarize, the issue that our team decided to address this semester was the deleterious effects of muscle function in spaceflight. Our solution to this issue was to create a compact blood flow restriction device that could be implemented into exercise resistance training in microgravity. Our device is called the HALIM, or hypertrophic aid by limb occlusion. Next is Carolyn to discuss the components of our device.
The current slide goes over the SolidWorks digital rendition of components used to make our current device. The cup is the main component of our device. It is sewn together using polyester thread and spandex and polyester fabric. The air cup was created using plastic and adhesives, and it was uniquely designed to go over our pressure and size requirements. Our Adafruit Metro Arduino was used to code and program our device. An Adafruit motor shield for Arduino was used as our motherboard. A rechargeable lithium-ion polymer battery was used to power our device. To control airflow in and out of the device, 4 DC motor units were used, 3 that allow air into the device and 1 that acts as a vacuum. Our device, called the HALIM, allows for blood flow occlusion by restricting
the vessels, and the targeted musculature. It is very durable and compact and custom made, therefore enhancing your comfort and performance. Here's Erin to go over coding.
For the coding portion of the device, the C++ language in the Arduino IDE software was used to program the hardware components stated by Carolyn earlier. The main goal for the code was to inflate an airbag to our desired pressure and maintain that pressure in order to achieve partial blood flow occlusion. When turned on, the cuff is inflated to a pressure of 145 to 150 millimeters of mercury. The pressure is measured by a pressure sensor connected to the air bladder itself. It does so by taking the atmospheric pressure and subtracting it by an absolute pressure to get the gauge pressure range of 145 to 150 millimeters of mercury. Once the pressure is reached, it is held for about 15 minutes. When this time frame ends, or if the device is turned off, the cuff will deflate. There are 3 DC motors used for the inflation portion of the device, located in the motor pins 1 through 3. While there's only 1 DC motor used in the deflation portion, located in motor pin number 4. The device is programmed when inflating, maintaining its pressure, and deflating to provide live feedback in numeral and graph form. Here's Micaiah to talk more about our testing.
To test our device, we recruited 2 adult females to complete testing with and without the Halo device. Before testing, participants were required to refrain from exercise for at least 5 days. Following this, there was a total of 3 sessions. On the first or intake session, baseline measurements were collected. On each exercise day, the protocol included a warm-up and 5 lower body exercises that astronauts complete today, including Romanian deadlift, back squat, deadlift, single leg heel raise, and single leg knee extension. The key differences, though, lie in the weights and the volume sets and reps in each protocol. The no Halo protocol consists of 24 reps over 3 sets at a higher intensity, while the Halo protocol consists of 75 reps over 4 sets at a lower intensity. After each exercise for this protocol, at least 1 minute of reperfusion allows for the restoration of blood flow. Notably, there was a blood draw that was taken approximately 2 hours after each exercise session, and there was a period of 5 days that separated each session. With our blood samples, we measure vascular endothelial growth factor. VEGF elicits the formation of new blood vessels, which increases circulation, allowing more oxygen nutrients into the muscle, which is crucial for muscular growth and recovery. Additionally, this increased circulation reduces arterial stiffness that's found in astronauts today. As you can see here, VEGF increased much more noticeably for one participant compared to the other. And this is just the prime example of the individualized response to exercise. Overall, Halo provides astronauts an innovative method for muscular adaptation. With the Halo, there is higher muscular hypertrophy with lower weights that can't be mimicked without our device. This allows astronauts to forgo remembering and following different sets and reps that comes with their current routine. And not only does the lower loads provide less stress on your joints, but it also reduces recovery time, allowing for enhancement of muscle recovery, all while making it easier, shorter, and predictable to complete their workout because of the timing that comes with our Halo device. Now here is Erin to conclude our project.
For the future directions of our project, the current materials in our air bladder are not what we envision for use moving forward. With access to higher quality polyurethane or PVC plastic materials, we'll be able to construct a device more suitable for high impact movements over a longer period of time. Secondly, blood flow restriction training is not just for unilateral resistance exercises. So by the addition of a second cup, you would be able to target both legs at the same time. Lastly, the current DC motors and batteries within the Halo device make our device functional in regards to inflation and deflation. But with implementation of stronger DC motors and a stronger battery, we will be able to make our cuff more efficient. In conclusion, we designed, fabricated, and tested the Halo device, which provides blood flow restriction during resistance exercises on site. Finally, we would like to take a moment to acknowledge people that have helped us along the way. To see our references, you can scan the QR code above. Thank you so much for listening to our presentation. Are there any questions for us?
Sorry if I missed this, but how does the solution simplify the set and rep pattern during resistance training?
Absolutely. So the astronauts are only given about 2.5 hours for a resistance exercise. With that, a lot of the time gets cut if anything important or detrimental happens throughout the day. Having a consistent rep scheme or rep prescription allows the astronauts to get what they need to get done in their workout. So with us, for a higher intensity workout, as we were kind of adjusting our results to, you would have to allow for more rest period. So 1:30 to 2 minutes for a rest period in between sets. While for us with the blood flow, it's about a minute.
Hi, can you go back to the slides about the results? I'm sorry, the other one though. The other one where it's more like compare by contrast about the yeah. That's something I want to ask about the musky and how they go. Like rest of it I get it, like it's not good with it, but why does a check mark on a heavyweight and a low weight? Why?
You can achieve through both. It's just our way with the blood flow restriction device is a bit more efficient for spaceflight.
But that's typically like heavier weight. I have additional advance with a halo though. If the person wanted to do with a like halo with a heavier weight, that's
No, that's a great question. So with the Halo device or with blood flow restriction, there are set protocols and guidelines that we have read and researched over the semester in literature. Therefore, the prescription is about 20 to 40% of their one repetition maximum. So that's why we're doing the lower weights. Typically, you can progress or do overload progression by doing 2% increase with every week.
So you guys said y'all wait 5 days before testing or between testing. Why couldn't you do like 1 day? Why'd you have to wait 5 days?
We waited for 5 days just because the biomarkers are still high. We wanted to make sure that there was kind of like a flush period through that biomarker so it wouldn't change the results for later. Great question, guys. We appreciate it.
So on the next slide, you showed 2 participants, but I was curious if you tested more than just 2 participants and looking at your diversity of male, female, and age.
Absolutely. I was waiting for this question. So due to our lack of time, we were only able to get 2 female participants. We also go to Texas Women's University, so the male population is very low, as you can expect. But with the time restraints, we were trying to access sedentary people to match the muscle atrophy rate that astronauts experience. So with that, we had a couple requirements that we had that not a lot of people our age or in our degree or even at our school fit.
Any other questions? All right, thank you, team.
Thank you, guys.
All right, next up from the University of Houston Clear Lake, it is the Space Cowboys.
Good afternoon, guys. My name is Dave Patino. This is Michael Chapa, and this is Abdul Lazar, and we are the Space Cowboys. Today, we will be talking about our TGSC, our contact sampling device. On this slide, you can see a small outline of our presentation, which consists of introduction and background, project goal and summary, criteria and constraints, research and conceptual design, modeling analysis, and future potential work. So for our mission connection background, obviously, through time, after the moon launching and we landed on the moon, space exploration has exponentially increased. So for this specific mission, NASA is preparing to go to the lunar South Pole. Astronauts will collect a variety of geological lunar samples. The objective is to gather undisturbed lunar regolith samples to facilitate in-depth research into various aspects such as grain size and material variety. So for our project, we had 3 requirements, which consisted of safety, materials, and functionality. So as we see above, we have 8 requirements within our safety requirements, which, for example, no pinch points, and any hazardous would be labeled as a no touch zones. For our material requirements, we only had 2, which consisted of having any component for our device to be part of the MBO approved material list, and any 3D components to have an infill of 75% or more. For our functional requirements, obviously, our device has to function and be effective, which has the large number. Like, for example, it has to be manually operational. It has to pass the ultimate tensile stress of 2.0. So for Team Space Cowboys, our project goals consisted of having a device lighter than 5 pounds, had a stowed volume of 8 by 8 by 16, NASA ideal, design a device capable of being open for study in an EVA suit, design a device that survives being dropped from a 4 foot above ground in lunar gravity. And our concept was to generate 9 unique ideas within 3 of us. And the final, obviously price-wise, design and produce a device under $1,000. Now I'll be passing on to Abdul.
Thank you, David.
All right. So based on some research, obviously I've already seen this from the previous presentation, the Apollo 16 actually used a contact sampling device. Basically how they used it was there was a beta clock at the bottom of the device that pressed into the lunar regolith and captured a sample of 0.1 millimeters. So this compared to our requirements, we need anywhere from 1 to 5 millimeters. Alrighty, so this is our house of quality. We just use this to gather our engineering metrics using the requirements given by the topic as well as engineering requirements. Now a little bit about our decision process. So each of us just gathered about 3 to 5 concepts. We just explained to each other with detailed drawings and put them into a decision matrix, as you can see here. So we came up with 9 different concepts and ranked them compared to our benchmark, which was that Apollo 16 contact sampling device. Just ranked them plus, minus, or 0. And our number 1 ranked was our RAM rod that we'll discuss a little more. But we did like our number 2 ranked concept, which is twist and go, which I'll discuss right now. So that is the model, just a base model of our twist and go. And basically how it works is there's handles at the top, gets placed into the lunar surface, twist it, and that's how it captures the sample. And it was actually inspired by, you know, the oxygen regulator on top of your typical grill. But the only thing with this was it was difficult for us to think about how we can properly capture the sample and keep it secure. So that's why we ended up going with the ramrod approach that Michael will get more into right now.
Thank you, Abdullah. So as he said, we went with the what we call the ramrod design concept, and this takes inspiration from your typical like fence building, like post digging tools. But essentially, you would place this device into the dirt, which then force lunar regolith up into the capturing chamber, and then that regolith would stay in contact with a piece of foam inside the cup. When the astronaut's ready, they would push apart the handles at the top, which would inversely push the clips at the bottom, which would then secure your sample inside the capture cup. When you're ready to review the sample, you can unclip the sample from the central base by pushing in on the tabs. Unengaging the foam from the cup, you can pull it back up so that when you twist it, it doesn't disturb the grain structure. Then you can twist the cap off and then look at your sample. We decided to make our device out of two materials. The first one would be 6005 T6 aluminum and tough PLA. We chose these materials because they are on the MDL approved materials list. Their structural capabilities is more than enough for what we need for this project, and they've been used in space before and are resilient to the wide temperature ranges that we do see. So components such as the central base and the handles will be made out of the aluminum, while the more intricate and geometrically complex components like the clips, the hinges, the capturing cup will be made out of the tough PLA. Our device as a whole does stay within the NASA desired stow volume of 8 by 8 by 16 inches, and it does come in at just under 5 pounds as well. And the total materials cost is just over $200. This right here just gives you an idea of how big our device is here. Like I said, with the components that are made out of the tough PLA, those will be 3D printed, so we can have rapid prototyping, because we do expect that kind of section to have the most iterations as we go on. And then the other aluminum components will be machined as well. So to figure out to look at the structural feasibility of our concept, we did do some simplified stress analysis, where we had to stay above the factors at least at 2 or above. So what we did is we did the maximum shear stress theory, where we calculate the effective stress and then compare it to the yield stress of the material that the components made out of. And that looks something like this. So we did simplify the geometry and apply some point loads, and that will allow us to figure out the stress on the components so we can get the final safety factor value that you can see at the bottom over here. Now I'll pass it back to Abdullah and conclude us with our forward work.
Thank you, Michael. So for our future work, so during the winter break, we plan to just gather the materials so we can just kick off manufacturing as soon as the semester starts. That includes rapid prototyping, so we can enhance our design, as well as the material machining. And we also want to do finite element analysis, and then get into our device testing. And in conclusion, our project is on track for completion, and we're going to take the lessons we learned in this event through TSGC and our professors, and use that for our next semester for when we're doing our manufacturing. So we do want to thank TSGC and also our professors, Dr. Billa and Dr. Hamidi, and we'll now take some questions. Thank you.
Questions for the team?
Just a quick question for you. So you mentioned the final design that you went with, that it was taken from the fence posting. Did you mention a depth that would be able to reach?
Yeah, so for the specification that they want us to have, we were designing for 1 to 5 millimeters is what they're looking for. So like in the past, they only got the basically residue 0.1 millimeters from the Apollo 16 concept. So the difference would be that they're looking for 1 to 5 millimeters. So I think the total volume that you would be capturing with our device, I think it's around 2 inches cubed or so.
And are you prepared for a lot of variety in the grain size, given the depth that you have identified?
We have researched some of the grain size. We're expecting. Can you repeat the question?
I'm asking about the grain size, given the depth of your, the ability for you to collect that sample, that depth. There's a lot of variety in the size of the pieces that you're picking up. So is that going to create a problem? Is that going to clog or?
It shouldn't create a problem. In some of our, in thinking my future iterations for design cut, we may want to do like a slightly different closing mechanism, maybe make it edged or so, just to cut it cleaner. But it shouldn't present a problem for the capture cut.
Thank you.
Did you have a down select process for the foam, for the canister foams or gels, for creating that resistance against the sinking?
Not yet. We're still the phone was kind of a new idea of recently, so we know we want to put some sort of cushioning pad there to protect the green, but we haven't looked at the type of foam yet. We know there's some foams that are allowed and not allowed on the MDL materials list, so we'll take a look at those and select the best one.
Any other questions? All right, thank you, team.
But also that's
Yeah, it was something like that. For some reason, cracks.
but
Demo season.
yeah. Oh. Yeah.
Okay, please welcome Dean Prager from UT Tyler.
Good afternoon, everyone. Welcome to our presentation. We are Team Prairie from the University of Texas at Tyler. Our project is a pH relation model for astronaut usage, which we call the pH guide. This is a slide showcasing the team, starting with Eduardo Blasio Jr., Agustin Garcia, Elijah Hicks, Delia Rodriguez, Brandon Portillo, and myself, Christian Simmons. Quickly, special thanks to our sponsors, Currently Justin, and our faculty advisor, Dr. Mohamed Biswas. Getting started with the background, where is the prototype needed? This prototype is needed in the International Space Station and is meant to be used on the microgravity environment. The prototype aims to monitor and regulate the pH levels of the ISS to be later used with the IVGEN mini system, which is appreciated in Figure 2. Now I'll pass it on to my teammate Agosto.
Great, thank you, Christian. So now we're talking about the concept statement. So what it is? It's a mini device with tubing and DAC system, and that is be connected to the to the IVGEN mini with right below to the filter assembly box. Now the requirements. So the requirements, we have 4 requirements. So we have the maximum dimensions, which is part of, think about it as in a lunch box. It's very, very small. For the maximum mass, we have our prototype should not exceed 0.77 kilograms. Now, for a communication system, we want our system to communicate with our astronauts. And the reason why is because we want to make sure that the pH is adjusted to the acceptable range, which is around 4.5 to 7.0. And finally, it has to be human safe. And the reason how we're going to do that is by make sure the output water will not put at risk or affect the human health, in this case with the astronaut. And by doing so is by choosing the buffer that it will not contain residual solvents without leaving that to 11.
Moving on to our selection of our primary pump for the system, we needed to make sure that our pump could maintain a minimum flow rate of 0.2 liters per minute. This is taking into account any inefficiencies or losses inside the pump, as well as losses caused by the tubing. So as you can see, the 2 primary variables we have to consider for our major loss and pressure drop are the length and diameter of the pipe, which is representative of the length and diameter of the tubing we're using in the system. Moving on to our 3D model of the selected concept. For testing and calibration purposes, you can see we have the 2 pH meters. The first one functions to give that initial signal to the microcontroller so it knows what the pH of the input water will be. The second one functions to get that final reading to ensure that we're within our range of 4.5 to 7.0. One thing you'll notice in our concept is the absence of a mixing chamber or mixing tank. So rather than having a tank with a pH meter that's continuously monitoring on a loop, we have it pre-calibrated so that the buffer solution is directly injected to the system. And this is something that we do to meet our time constraint. Moving on to our functional diagram of the system, you can see everything will be powered either through the Arduino, or if it requires too much power, the Arduino can't supply, it will have its own supply with batteries externally. pH sensor 1 sends that initial reading that I mentioned to the microcontroller. It will be pre-calibrated to signal pump 1, which is our mini peristaltic pump that will be used to be dosing the system with our buffer solution. Pump 2, which is our standard peristaltic pump you see here, that one functions simultaneously throughout the process to have our fluid just running through the entire system. Near the end of the system, we have our flow meter after all of our losses to ensure we're still maintaining that 0.2 liters per minute minimum. That's pH sensor 2. That's making sure we're, after our calibration and after our pH correction, we're still within the acceptable range. And all the information from pH sensor 1, as well as 2, and our flow rates will be displayed directly on our LCD screen so that while the prototype is operating, we're able to easily monitor that.
So next we'll be talking about the testing plan. So for the testing plan, we have our testing objective, and it's to ensure that calibration, the pH system correction, to ensure the pH system performs reliably and accurately. And then next we have our testing scope. So our testing scope discusses calibration, validation, and performance of the pH system components. And in our components, our key components to test, it's going to be the pH sensor, the flow meter, the peristaltic pump, and the air-free water flow filter. And then next, we'll be discussing the next slide. So the next slide is going to be the component specifications, and displayed on the table is our main components, which is going to be the pH sensor, the pumps, the LCD screen, the microcontroller, the flow meter, and the filter. And displayed as well as the current and the technical specs of each component. And next, I'll pass it to my classmate, Yadira.
Right here, we have the timeline where we show tasks that have been completed and as well tasks that are ongoing. So far, the team has successfully completed team profile, midterm report, and final report, poster, and video. And by the end of today, we'll be done with the showcase. Next ongoing task is going to be the UT Tyler design review, in which the team will prepare extensively to present to the faculty at UT Tyler. Next slide, please. Right here, in conclusion, the main takeaway of our prototype and design is that it will monitor and regulate the pH level within the system to ensure that we stay within the safety range. Next, it's going to be automated by software. So the software that we're using is the Arduino, and the Arduino will analyze, provide data within about the pH, and correct the pH to the safe level. Lastly, the team has extensively researched which type of junction will take less time to stay within the time parameters given by our project within 5 minutes that the pH needs to regulate. And the mixing junction will for sure be the right choice for that as well. Take less space and will ensure that we stay within a light weight for our whole entire prototype. Next, I'm going to give this to Brandon, my classmate, that will be talking about future works.
For our future works, we'll be mainly focused on refitting our design with lighter, more cost-effective components, as again, weight is a factor for the ISS space shuttle, along with identifying possible modes of failure among our design and ways to mitigate the likelihood of those events of failure happening. And also, finally, through our final design, implement medical-grade materials. I would like to thank our advisor, Dr. Mohammed Biswas, for his insightful advice, NASA as Courtney Shurko and Austin Yang for guiding our project, and finally, to the Texas Space Grant Consortium for giving us the opportunity to work on this design challenge. Thank you.
Questions for the team?
Yeah, sorry, maybe I missed it, but I didn't see a flow diagram, or how do you adjust the pH level real time? I mean, is there a flow loop, and what are you using to adjust? Like the other team had 2 chemicals that they would put in to adjust the pH.
So that's something we covered in the, I guess, the 3D concept. Rather than having some type of loop where it's continuously adjusting like you're mentioning, the idea is to pre-calibrate the system. So instead of, since we're on the time constraint, instead of just having a continuous loop in a tank, you see, take a pH reading, adjust if it's out of range, take a pH reading and adjust again. We're gonna pre-calibrate the system. So it sees a specific pH. We're always gonna have 1 liter of water, then it knows exactly how much a buffer solution should be injected.
So you have like a tank or reservoir?
We're actually moving away from the tank or reservoir. We have a mixing junction, so rather than mixing inside of a tank and keeping on doing the pH readings, it knows what buffer solution should be injected for any given pH reading.
All right, other questions?
So y'all were talking about your buffer solutions, but maybe I missed it. I don't remember y'all saying which buffer solutions y'all have chosen. Is that something y'all are leaving up for the future, or do y'all already know what y'all want to use?
That's somewhat half and half for future work as well as some considerations. We have a few that we're looking into now, one of which is a combination of sodium citrate and citric acid. That'll be used to lower our pH, but as of right now, we haven't decided on one specific.
So you mentioned moving away from like a tank. I would imagine as you're trying to balance the pH level with the volume kind of plays it back to like the fluid that you're working with. How would you, if you don't have like a set volume, how do you sort of determine how you know, add in a certain amount of acid base to balance that out?
That's a good question. For our specific application, we do have a set volume. So every single batch that runs through our prototype, it's going to be in line with the IVGEN Mini. It runs in 1 liter batches. So that is one consideration. If we did have a variation in volume input, we wouldn't be able to just pre-calibrate it. But since we do always have that 1 liter, that's just a constant. All we need to take into account is the pH of that single liter.
All right, any other questions? Thank you, team. All right, let's give all our afternoon presentations one more round of applause. All right, so now we have another poster and model session for everyone to wrap up the judging if they haven't finished that. We've got some snacks in the back. We've given ourselves a good hour to tally all the judges' scores. So we'll be back here at 4:30 to see the results.